Welcome to another episode of Science Simplified. In today's video, we're diving into the fascinating world of black holes. Get ready to unravel the mysteries of these cosmic wonders in just 10 minutes. Black holes are some of the most enigmatic and mind-boggling objects in the universe. But fear not, because by the end of this video, you'll have a clear understanding of what black holes are and how they work. Remember to hit the like button and post a comment to participate in the discussion, and subscribe to Science Arena for more interesting science material. So, what exactly is a black hole? Imagine a region in space where the gravitational pull is so incredibly strong that nothing, not even light, can escape its grasp. This intense gravitational force is created when a massive star collapses under its own weight during a supernova explosion. The key characteristic that defines a black hole is its event horizon. Picture it as an invisible boundary surrounding the black hole, much like a cosmic force field. This boundary marks the point of no return, beyond which anything that ventures too close is inevitably pulled into the black hole's gravitational grasp. Imagine you're floating in space, approaching the event horizon of a black hole. As you get closer and closer, the gravitational pull becomes increasingly stronger. At a certain distance, if you were to fire up your spaceship's engines at full throttle, you could still manage to escape the black hole's clutches. However, once you cross that critical threshold known as the event horizon, the situation changes dramatically. Once you cross the event horizon, it's as if you've entered a gravitational point of non-rescue. The pull of gravity becomes so overwhelmingly intense that not even the fastest spaceship or the most powerful engines can save you. No matter how hard you try to fight against the gravitational force, you're destined to be inexorably drawn towards the heart of the black hole. Think of it as being caught in a swirling cosmic whirlpool, where escape becomes an impossible dream. The event horizon acts as an impenetrable barrier, sealing your fate within the black hole's gravitational prison. The concept of the event horizon is truly awe-inspiring and perplexing. It signifies a boundary where the laws of physics as we know them cease to apply. It's a point of transition from the familiar rules of our everyday experience to the extraordinary realm of extreme gravity and warped space-time. But let's dispel a common misconception. Despite their name, black holes are not empty voids or holes in space. Quite the contrary, they harbor an extraordinary amount of mass packed into an incredibly compact volume. Picture them as super-dense objects with a gravitational force so unfathomably strong that even time itself is significantly affected in their presence. To understand this concept, let's imagine a typical star. Stars are colossal celestial bodies made up of hot, glowing gases, fueled by the process of nuclear fusion. The immense energy generated from the fusion of hydrogen atoms into helium counteracts the inward pull of gravity, maintaining a delicate equilibrium. However, when a massive star exhausts its nuclear fuel, it undergoes a cataclysmic event known as a supernova. The star's core collapses under its own weight due to the relentless force of gravity, crushing matter into an incredibly tiny space. This collapse is what gives birth to a black hole. As the star collapses, its mass becomes increasingly concentrated, squeezing the matter together to an extraordinary degree. The result is an object with an incredibly high density, far beyond what we encounter in our everyday experience. To put it into perspective, a black hole with the mass of our Sun would have a radius of just a few kilometers. This mind-boggling density gives rise to the unimaginable gravitational force exerted by black holes. The gravitational pull near a black hole is so overpowering that it distorts the very fabric of space-time. In fact, it bends the path of light and alters the flow of time itself. Imagine standing near a black hole, peering into its abyss. The gravitational force at your feet would be significantly stronger than the force at your head, due to the intense gravitational gradient. This phenomenon, known as tidal forces, can stretch and squeeze objects to their breaking point, and ultimately tear them apart. It's an indication of just how extreme the gravitational forces near black holes truly are. One of the most mind-bending concepts associated with black holes is time dilation, a consequence of their extreme gravitational influence. Time dilation near a black hole's event horizon is a fascinating phenomenon, as it reveals the profound effect that gravity has on the flow of time itself. To grasp this concept, let's consider two observers. One situated far away from a black hole, and the other falling towards the event horizon. As the observer near the black hole crosses the event horizon, something extraordinary occurs. Time for them begins to slow down significantly compared to the observer situated at a safer distance. From the perspective of the observer far away, time appears to pass at a much faster rate for the one falling into the black hole. It's as if the fabric of time itself is being stretched and distorted, creating a stark contrast in the passage of time between the two observers. Imagine a scenario where the falling observer experiences only a few minutes before crossing the event horizon, while the observer far away witnesses hours, days, or even years passing by. This time dilation effect near a black hole's event horizon is akin to a cosmic time warp, where the flow of time is drastically altered by the immense gravitational field. This phenomenon arises due to the profound warping of space-time caused by the black hole's gravitational pull. Gravity bends and curves the fabric of space-time, creating a gravitational well around the black hole. The closer one gets to this well, the stronger the gravitational field and the greater the time dilation effect. The reason behind this time dilation lies in the fundamental nature of space-time. According to Einstein's theory of general relativity, mass and energy warp the fabric of space-time, influencing the motion of objects and the passage of time. In the vicinity of a black hole, where the gravitational field is exceedingly intense, this warping becomes exceptionally pronounced. As an object falls into a black hole, it experiences an increasingly stronger gravitational pull. This causes time to slow down for the falling object relative to observers situated in areas with weaker gravitational fields. The deeper the object ventures into the black hole's gravitational grip, the more pronounced the time dilation effect becomes. As matter and energy succumb to the powerful gravitational pull of a black hole, they often form a remarkable structure known as an accretion disk. This disk is a mesmerizing sight, a swirling disk of superheated particles that orbits around the black hole, gradually spiraling inward. The formation of an accretion disk begins with the capture of nearby matter. This matter can come from a variety of sources, such as a companion star in a binary system or interstellar gas and dust that happens to come too close. As these materials approach the black hole, they encounter its gravitational force, causing them to lose angular momentum and fall into orbit around it. Once trapped within the gravitational grasp of the black hole, the captured matter begins to revolve around it in a flattened disk-like structure. This disk is comprised of an immense number of particles, including gas, dust, and even larger objects such as asteroids or planets. These particles spiral inward due to friction and gravitational interactions, constantly replenishing the disk as they collide and merge. The particles within the accretion disk undergo extreme heating and compression as they move closer to the black hole. The intense gravitational forces and the tremendous friction generated by their rapid motion cause them to reach staggering temperatures. The disk becomes a seething cauldron of superheated matter, emitting intense radiation across a broad spectrum, from X-rays to visible light. The radiation emitted by the accretion disk makes black holes some of the brightest objects in the universe, despite their reputation as dark devourers. This radiation can outshine entire galaxies and can be detected by powerful telescopes and instruments designed to study the cosmos. The exact nature of the emitted radiation depends on various factors, including the mass of the black hole, the rate at which matter is accreted, and the properties of the surrounding environment. For instance, as matter spirals closer to the event horizon, it reaches incredible speeds, generating strong magnetic fields that further shape the behavior of the accretion disk. But what happens to the matter that falls into a black hole? Well, it's believed that it becomes part of the black hole itself, adding to its mass and making it even more powerful. While black holes are often thought of as celestial vacuum cleaners, relentlessly pulling matter and energy into the gravitational grasp, they also have the astonishing ability to unleash mind-blowing phenomena known as jets. These jets are dramatic displays of power, shooting out from the black hole's poles and propelling energy and matter into the vastness of space at incredible speeds. The formation of these jets begins within the vicinity of the black hole's accretion disk, where matter swirls in a frenzied orbit. As particles near the event horizon, some of them are fortunate enough to escape the gravitational clutches of the black hole. However, they don't simply drift away. Instead, they are caught in the grip of the black hole's intense magnetic fields. The exact mechanisms behind the formation and launching of jets are still not fully understood, but scientists believe that the strong magnetic fields in the vicinity of the black hole play a crucial role. These magnetic fields become highly twisted and wound up due to the rotation and accretion of matter. As matter interacts with these twisted magnetic fields, a tremendous amount of energy is unleashed. This energy propels some of the particles along the black hole's axis of rotation, accelerating them to extraordinary speeds. The particles are expelled in the form of narrow, focused beams that shoot out from the black hole's poles. These jets can extend for vast distances, often spanning thousands or even millions of light-years. They carry an immense amount of energy and matter into the surrounding space, leaving a lasting impact on their cosmic surroundings. The energy released in these jets is truly mind-boggling. They can emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays and even gamma rays. In fact, the energy output from these jets can be so intense that they outshine entire galaxies, making them visible from great distances. The phenomenon of jets from black holes has profound implications for the evolution of galaxies and the cosmos as a whole. The energy and matter carried by these jets can influence the dynamics and properties of the surrounding interstellar medium, triggering the formation of new stars and affecting the growth of neighboring galaxies. They are vital players in shaping the cosmic landscape and driving various astrophysical processes. That's all for this episode of Science Simplified. We hope you enjoyed this journey into the realm of black holes. Stay curious, and join us next time for another exciting exploration of hard science topics in plain and simple language.